Derek asked me to talk about GC testing and the purity of essential oils, and I said, really? Are they really going to sit through GC testing? But yeah, that's what he wanted, so that's what I'm going to talk about. This is a project that we started in the middle of last year. Derek wanted to test the essential oils from Essential Depot, so he donated chunk of money to Hampton-Sydney College, which helped us to buy a new gas chromatograph. And now I'm going to explain what we do with it. So first, I have to say, what is an essential oil? Probably most people here know what an essential oil is, but there are lots of fragrances that aren't essential oils, so I want to be clear about what we're talking about. First of all, it's volatile. What does it mean that it's volatile? Many people think volatile means explosive or dangerous, but to a chemist, the word has a very specific meaning. All it means is it easily evaporates. It comes from volare, to fly in Latin. All it means is that it's easily evaporated. And if you think about it, how could you smell something that isn't easily evaporated? It would never get to your nose. And so maybe you would psychically have a psychic smell, but if you want a real smell in your nose, it has to be volatile. It's derived from some part of a plant. There are lots of fragrances that aren't, so we're talking about specifically something that comes from a plant. It carries the odor or flavor of the plant, and it's usually a complex mixture of aroma chemicals. We'll talk about specifically some of the usual players. So now I need to talk about purity, and again, chemists always use words very precisely. In common language, the word pure is talked about all the time. So you talk about, how about milk? Pure milk. What is pure milk? It's milk that doesn't have some non-milk thing in it, right? That's what we mean. That's what ordinary people mean by pure, but a chemist has to make it more difficult than that. A chemist would never talk about pure milk because milk is already a mixture of different things. So we reserve that word for things that are only one thing. So there are compounds and there are mixtures. And you're familiar with some things that are compounds. Compounds have formulas. They have chemical names. So water is a compound. Salt is a compound. Sugar is a compound. So water has a formula, H2O, and a sugar that you may be familiar with, fructose, is also a compound, has the formula C6H12O6. Those are all pure substances. When I mix sugar and water together, I get a strange thing called honey, and you might say, oh, this is pure honey. And what you mean is it doesn't have cane sugar added to it or something, but a chemist would never talk about pure honey because honey is already a mixture of fructose and water. Instead, I would use, for a mixture like that, I would use the word it's genuine honey, it's authentic honey, it's unadulterated honey. I would use all those words to describe honey, but I wouldn't talk about purity. All right, there's the word. A terrible polysyllabic word, and I want you to at least appear to be intelligent, and the first step is even being able to pronounce a word like this. So this is chromatography. 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 Let's practice it. Chromatography. Chromatography. And so, you know, if you're going to talk to people about chromatography, you ought not to stumble over the word. So you might go to a dark corner somewhere and practice. And if you don't, but look, if you say GC, I'm the GC this, I'm the GC that, and somebody says chromatography, you say chromatography, it just marks you as a charlatan. You know, you've been throwing about GC like you know what you're talking about. You can't even say the word. So practice that. It's a technique for separating mixtures into their components. So for example, you might do chromatography on honey to separate it into the sugar and the water portion. So we're going to do a demo now on all the project tables. You have a mason jar with some water in it, and you have a paper towel. This is a high-tech demonstration. You have to order this online. It's very expensive, but I just used paper towels that I happen to have in my kitchen. At the bottom is a pencil line, and there are 4 dots here. These dots are from Flair felt tip pens. So I have a purple dot, and a pink dot, and a green dot, and a mystery dot. And I wrote the names of these in pencil because I'm about to put it in water, and I don't want my information to run, so I wrote that in pencil. So to get this started, you need to take your paper towel and kind of roll it into a little tube so that it'll fit down in the mason jar. We don't want the water line to be above the pencil mark. We want the water line to be down here so that the water wicks up through the paper. You're not just dipping it in. You want it to stand up so that just the very bottom of the paper gets wet. And we're going to no, don't just leave it in there. We're going to leave it's going to take probably a half an hour to do its thing, and we'll visit it from time to time. But you can see some of you, the ink is already starting to run, but it's running in a very interesting way. Yeah. Anybody need another one? I got one more. Okay, so I really can't get away from the nerds and cheerleaders. Everybody here has probably heard the nerds and the cheerleaders, but it's become kind of an obligatory thing. Everywhere in the universe, there are nerds and cheerleaders at high school cafeteria tables. They always separate it into the nerd table and the cheerleader table. Somebody who doesn't know might think that nerds hate cheerleaders, and that isn't true, because I knew cheerleaders and they like me just fine individually. And you might think nerds hate cheerleaders, but that's not true because I love cheerleaders. So it's not that the nerds and the cheerleaders don't like each other. It's that the cheerleaders prefer the company of other cheerleaders to the company of nerds. You might think the nerds also prefer the company of other nerds to cheerleaders. It's not true. It's simply that when a nerd goes to sit down, if he sits down at the cheerleader table, every cheerleader at the table can't help thinking, it could have been another cheerleader sitting there. So where the nerds sit, wherever there are empty seats. And so the nerds tend to congregate, the cheerleaders separately. But that's not what I'm talking about. That's just a kind of preamble. Because now I want to talk about the cheerleader wedding reception. And at the wedding reception, there's a receiving line with the bride and the groom and their parents and all the bridesmaids and everything. And in order to get to the food, you have to run the gauntlet of this receiving line. So let's imagine now the cheerleader wedding reception and the couple of nerds that got invited. By accident? I don't know. Somehow the nerds wound up at the cheerleader wedding reception. Who's going to get to the food first? The nerds or the cheerleaders? Why is that? Because at the receiving line, every cheerleader is going, oh, where'd you get your nails done? Oh, your hair is so beautiful. It takes 20 minutes to get from one person to the next if a cheerleader is talking to another cheerleader. But if a nerd comes, nerd's like, hey, what's up? And the thing is, to make this allegory work, it's necessary that you imagine that in the etiquette of this receiving line, it's okay to cut. So the cheerleaders are all lined up. They're gabbing about all kinds of cheerleader things. And the nerd comes up and says, hey, yeah. Hey, how you doing? How you doing? And the nerd gets quickly through the receiving line, has already finished eating before any of the cheerleaders have gotten through the line. All that's necessary is the cheerleaders have greater affinity for other cheerleaders than they do nerds. And so when it's a cheerleader receiving line, the nerds move quickly and the cheerleaders move more slowly. You could have the opposite situation, the nerd wedding reception, with a couple of cheerleaders that have gone invited, and the same thing would happen, because the nerds are all talking, hey, did you see that chess game the other day? You know, they're talking about all kinds of nerd stuff. The cheerleaders are like, yeah, hey, what? And so the cheerleaders get through very quickly, and the nerds are kind of working their way through the receiving line. So that allegory is going to serve us well when we talk about the C word. Chromatography, very good. There's 500 guests. If there's 250 nerds and 250 cheerleaders, the nerds will get through first. So, we have the same thing going on here, but it's not nerds and cheerleaders. We've got water and paper. And some of these inks have a greater affinity for the water. Some of the inks have a greater affinity for the paper. And so the different colors of ink move at different rates as the water moves up through the paper. We're going to call the paper the stationary phase because it stays still, and we're going to call the water the mobile phase. Now these pens are all water-soluble inks. They're Flair felt tip pens. But I could do the same thing with permanent markers, but I would need to choose a different stationary and mobile phase. I wouldn't use water as the mobile phase, because how about permanent marker and water? Never going to move. I'd have to use a different solvent like alcohol in order to get a permanent marker to do the same thing that we're seeing here. Compounds with greater affinity for the water move quickly. Things with a greater affinity for the paper move slowly. Now we're going to add a word to it, gas chromatography. So now we're talking about not water and paper, we're talking about volatile things. We're talking about things that are easily turned into the vapor. The stationary phase is a thin glass tube. It's bigger than a human hair, but it's not much bigger than human hair. It's a very thin, long glass tube, and it's so thin that you can bend it. I meant to bring a piece, but I forgot. You can bend it, and it actually comes as a coil. It's wound up on a little metal thing to hold it in place. The column that we're using is 30 yards long, and it's about 1/10 of a millimeter in diameter. It's very, very thin and very long. And it's not just a glass tube, because the glass tube has to have something in it, the stationary phase. And there are lots of varieties for what the glass tube could be coated with on the inside. There are lots of choices, and it depends on what is it that I'm analyzing, which stationary phase I'm going to choose. The mobile phase is helium gas. We have a steady supply of helium gas flowing through the tube, and as when the molecules are injected onto the column, they will move at different rates, depending on their affinity for whatever stationary phase that I've chosen. This whole thing, the glass tube and everything, is inside an oven, and I can program the oven to start out at one temperature and to ramp at a certain rate until it reaches the final temperature, so that things that are not very volatile won't move very quickly when the oven is cold, but they will move more quickly when the oven is hot. Okay, this is what it looks like. We have the GC on the right and the mass spec on the left. I'm going to talk about mass spec later. I'm going to zoom in now. Boom. There's the GC part of it. You see that coil is the column. I have an injector. I use a syringe to inject a sample onto the column. And it moves slowly or quickly through the glass tube until it vents out the back end, just like the receiving line at the wedding. This is our GC, it's a GC mass spec. I'll talk about the mass spec later, but you've seen this probably if you ever watch NCIS. It's not just that Abby has a GC mass spec, it has a name, major mass spec, and not only that, we have the same one. It is the same model that Abby uses on NCIS. It's very, very noticeable because it has that circle there on the left. When I saw it, I thought, ha, that's the one we have. So on the right is the GC, on the left is the mass spec, and I'll talk about those two parts separately. Okay, this is what a gas, here's another word for you, chromatogram. It's easier than chromatography because it has fewer syllables. This is a gas chromatogram, and all it is like a visual display of that receiving line. So the things that come out early, like 6.5 minutes there, the things that come out early are the nerds at the cheerleader reception. And the things that come out late are the cheerleaders at the cheerleader reception. It took them longer to get through the column into the mass spec, which serves the purpose of our banquet at the wedding reception. Okay, old school GC, we didn't have mass spec. Mass spec is something that we didn't have when I was growing up. So all we had was GC, and all we really knew was how long does it take for this compound to move through the column. So you get a bunch of pure chemicals, pure using pure in the way that a chemist uses the word pure. You inject them onto the column, squirt them one by one onto the GC. You measure how long does it take to get through this glass tube. That's called the retention time. And then you make a table. This compound takes this long, that compound takes that long, and anytime you see a peak at 6.543 minutes, you know, oh, that's that compound that takes 6.543 minutes, and you come up with a list of all the compounds that you're interested in and how long they take to run the gauntlet. So this is an example of just a GC report. Beta-myrcene takes 6.543 minutes. D-limonene takes 7.219 minutes. And caryophyllene takes 13.056 minutes. Just by measuring the retention time, I can identify the compound. But there's a problem with the old school method. What if your mixture contains a new compound that you've never seen before? How are you going to identify that? How are you going to even begin in the infinitely many chemicals that there are? How are you going to even know which one I should search for? Second thing is, what if two different compounds, have the same retention time? They're going to come on right on top of each other. How are you going to know which one is which? So we're back to the GC. We're going to move from the GC part to the MS part. This is a block diagram for the mass spectrometer, and the idea is we're going to squirt whatever it is that's coming off the column into a vacuum. We're going to bombard it with an electron beam. You can imagine shooting a machine gun at it, and that's going to fragment the molecule into parts. And then the mass spec part, the rods there, are going to determine the mass of each of the fragments. It's this crazy, crazy way to identify a molecule. But you know what? You can't just look at a molecule and see what it looks like. You have to be able to measure something about it. And the mass is something that can be measured. So I'm going to talk about fragmentation patterns. If you were shown a demolished vehicle, would you be able to identify it? So you got a pile of car parts there. Can you tell the difference between a Toyota Corolla and a Tacoma? It's just a pile of car parts. Now you might not know, what is a Corolla? It's a small sedan. It's a small sedan. What is a Tacoma? It's like it's a little pickup truck. It's not a giant pickup truck. They're sort of the same size. And so you're looking at a pile of car parts there. Imagine, though, that you notice that in amongst the pile of car parts was a tailgate. Can you identify it now? Yeah. Yeah, that's probably okay. I can probably say, okay, that's a tailgate. It's got to be a pickup truck because a Corolla doesn't have a tailgate. Now, you might also look, oh, there's the Toyota logo, and look here, it says Corolla right on it. But the molecule doesn't have that. All it has is the weight. So now imagine you aren't able to see a tailgate. You're only to see, here's a piece of a car that weighs this much. Here's a piece of a car that weighs that much. Here's a piece of a car that weighs that much. And if you looked at a Corolla and a Tacoma, you would find things that weigh different amounts. If you're looking at the steering wheel, how about the weight of the Corolla steering wheel compared to the weight of the Tacoma steering wheel? Probably about the same. And you know what? You never find half a steering wheel. When you demolish a car, basically the steering wheel comes off all as a part. You never find half a tailgate. The tailgate came off as the tailgate. The door, the windshield, all these parts came apart intact. Can you tell it from a Highlander? What is a Highlander? Yeah, so a Highlander is much bigger than a Corolla. You add up all the parts. Oh my God, if you can't tell a Highlander from a Corolla, you're not trying very hard, because physically the pile is just bigger, the parts weigh more, and there are more weighty parts when you add them up. How about from a Camry? Camry and a Corolla, kind of similar cars. Camry, an infinitely superior car. That's what I drive. I looked at the Corolla, it just wasn't up to snuff. Camry and Corolla, Camry is a little bit bigger car. Its door, the Camry door weighs more than the Corolla door. And how about a Civic? Okay, look, these are almost the same car. The Toyota Corolla and the Honda Civic are Honda and Toyota's attempt to reach the same market. The doors gonna weigh kind of similar. The windshields, the steering wheels, kind of similar between those two cars. If you just had a pile of car parts and their weights, could you tell a Corolla from a Civic? You know, if you had demolished both cars and weighed all the parts, you might be able to tell the difference, but you would have to scrutinize it a little more carefully. All right, now we're talking about molecules. We're going to demolish a molecule. What are the parts? So this molecule is ethylbenzene. I don't care that you know the structure of the molecule, but it's a ring with stuff hanging off of it. So the whole molecule is on the right there. It's a 6-membered ring with CH2, CH3 hanging off of it, 2 carbon atoms. If you add up the weight of that molecule, it adds up to 106. But if you knock the CH3 off of it, that's like removing the steering wheel, it only weighs 91. You're going to find a mass peak at 91 and 106. You aren't going to find one in between, because that would be like removing half a carbon atom, which just doesn't happen when you're demolishing a molecule. There's a more complicated molecule. I don't know if I can even pronounce this. 3-pyrid blah, 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 blah. I don't even care. I don't even care if you can pronounce it. It's a big honking molecule. And when you fragment it, it fragments into the things that fall off easily, and that means you break a bond. So here I have the whole molecule all together is 369 mass units. But if I chop off that last little piece, it only weighs 298. And if I chop off a couple more, it's 272. And you can identify in green the mass fragments that you would expect to see for a molecule like this. Okay, so now we have the NIST library, which NIST is the National Institute of Standards and Technology. They have a mass spectral library that a computer can search, so when you see a fragment pattern, it can look and see what molecules have fragment patterns similar to that. It's automatically searchable, so we love this library. What was it? 242,466 compounds in the library, which is really, really nice. We have problems with mass spec. We always have problems. What if 2 compounds have similar fragmentation patterns? That would be like the Corolla and the Civic, very similar fragmentation patterns. And again, what if the compound that you're trying to find isn't among the 242,000 compounds in the database? Okay, so this is a mass spectrum of alpha-pinene. I don't even care that you know what alpha-pinene is, but when you smash it apart, it falls apart into these fragments. And I'm going to show you a similar fragmentation pattern for beta-pinene. There's beta-pinene. I'm going to use 2 hands now. Alpha-pinene, beta-pinene, alpha-pinene, beta-pinene. You see they're very similar, but they're not identical. What do you see as the difference? Alpha-pinene, beta-pinene. They have the same fragments, but they have different numbers of those fragments. So beta-pinene, look at the peak at 42. Short in alpha-pinene, tall in beta-pinene. So if I were really, really careful, I might be able to tell the difference between alpha and beta-pinene, but they're so similar, it's kind of hard for the computer to look at these and say, the thing that you're interested in is actually alpha-pinene. But alpha and beta-pinene have different retention times. Alpha-pinene comes out first, beta-pinene comes out second. So while their mass spectra are very similar, their retention times are quite different. 5.66 minutes compared to 6.93 minutes. So if I have a doubt now, I'm looking at a mass spectrum, I look at the retention time and I'm trying to match what I'm looking at, does it have the right retention time, and at the same time, does it also have the right mass spectrum? And those two together will be a pretty bulletproof identification for a compound. I also have compounds that have the same retention time. Okay? In the old school GC, very hard to tell the difference between D-limonene, beta-phalandrine, and eucalyptol, because they come out at like 7.2 minutes. They're right on top of each other. But their mass spectra are very different. D-limonene, the tallest peak is 68. Beta-phalandrine, it's 93, and eucalyptol, it's 43. So even though their retention times are very similar, their mass spectra are very different. Combining the two, GC and mass spec, gets me identification for a compound that I can rely on. Okay, when you go to the Essential Depot website now, when you look up an essential oil, you'll be able to look at the GC report for not just in general lavender oil, but a batch specific. This batch of lavender oil that we're currently selling right now has this GC, and you can tell how much of each of the components is in it. So this one has 0.45%. The one we're looking at is the area percent, and of course that's very small. So here it is blown up. 6.54 minutes, we've got 0.45% beta-myrcene, 0.7% limonene, 4.63% eucalyptol. If you think about lavender oil, what is it mostly? It's mostly linalool and linealyl acetate. Pretty much all lavender oils will have those two, and the other things that they have depends on what country is it from, what season was it grown in, how was it distilled, all the various things that go into a lavender oil. Thing I want to show you though is that this is multiple compounds. It's not pure lavender oil because it's already a mixture, and the composition varies from batch to batch. What I've listed here, I think, are 16 compounds. How many compounds are there in lavender oil? The answer is, it depends on how hard you look. Because the mass spec will find, if you want to find out to 1/100% all the compounds that are there, even 1/100%, the GCMS will do that. What we've decided mostly is to settle on 15 compounds for identifying the authenticity of an essential oil. But a lot of places they do 100 compounds and then they're left with a giant list of all the possible things that are in it. We're thinking this is a little bit more understandable if you're just trying to get a snapshot of this particular batch of oil. Question?
So ideally, the less compounds, like an essential oil like lavender has, the better quality? Or
No. So that's, I can't, the question is, so the fewer the compounds there are, the better the lavender oil is. No, you couldn't be farther from the truth. And you also can't say the more compounds there are, because you know what? All I had to do was click a button. I could have found 100 compounds instead of 15. So how do you know whether this is a good lavender oil or a bad lavender oil? You have to come back tomorrow, because that's what I'm going to be talking about in tomorrow's lecture. Is now that we know about GCMS and what the report means, how do we look at a report and decide, can't say pure lavender oil, what will we be looking for? an authentic lavender oil, a genuine lavender oil, an unadulterated lavender oil? How do we know whether this is good lavender oil or bad lavender oil? So, yeah, another question.
Those numbers, those percentages that you've identified and were on the last slide, are those constant as long as in that batch?
So, in this, the question is, the percentages, are they constant in the batch? So, for example, if I took 8 different bottles from the same batch, would I get the same percentages? There's going to be a little bit slop. One of them might be 0.45%, one might be 0.46%. Would you say that's a problem? Probably not. If I got 0.45% from one bottle of the same batch and 27.2% from the other, something's wrong. That doesn't add up. That's not. And even if I took the same sample and injected it 12 times, would it always come out 0.45%? No, it's probably going to vary a little bit around. There's going to be a little bit of slop from one measurement to another. Yeah.
I had a question on it. Aren't essential oils kind of like a wine, though? You know, it's all by opinion whether you know, for instance, a lavender, you know, if you prefer that particular scent and, you know, over another one maybe that has a baser scent to it, you know.
So the question is, isn't it like wine tasting where you got this expert and that expert and one of them likes the wine and the other thinks the wine is terrible? There's a little bit of that, but what I'm going to talk about tomorrow will help us to decide what do we mean by an authentic lavender oil. So it's a great question. Hold on to it for 24 hours and let it mature like a fine wine. I saw another hand, yeah.
Are the results similar from one batch from another batch, like different batch numbers?
No, they could be quite different. And so you're saying now, so for example, I could have an authentic lavender oil and the next batch that comes in is adulterated. Well, you wouldn't expect those to be the same, and we'd like to be able to tell them apart. But even if I had 2 different samples of a genuine lavender oil, they may be quite different, and you'll be surprised at how different they can be. I'll be talking about that tomorrow, and you'll see.
Is that like a report from a genuine lavender oil?
So it's not enough to have one. I need multiple so we can compare. For lavender oil, for example, I compare Essential Depot lavender to 42 different lavender oils. Because there's variation, 42 genuine lavender oils that are all different from one another. And now how do I tell whether this lavender oil that I'm looking at right now fits among the 42 other lavender oils? So again, I'll be talking about that tomorrow.
Kevin, when
Yeah.
you're talking about the 42, you're talking different types of lavender,
Lavender from Bulgaria, lavender from France, lavender from the United States, lavender from Bulgaria in the wintertime compared to the summertime, compared to northern Bulgaria, southern Bulgaria.
Even the time of day on the same plant.
And again, it could even be that this is the same plant grown in the same field sent to 2 different distillers, and they're slightly different because the distillation process was a little different.
the length of time you're supposed to, you're going to get inferior oil.
So all those things come into play and make the job of deciding whether it's authentic or not a much trickier question than you might think of at first blush. Okay.
Hi. So if you have a batch of soap that you put lavender oil in, you shouldn't list it pure lavender oil. You can't.
So everybody knows what pure means. If you use the word pure, everybody knows what you mean. But a chemist has a specific meaning to that word. And so personally, I don't talk about pure lavender oil, but I understand that, you know, people outside of chemistry, they were using the word before chemists were. So I don't really have a right to tell them that that meaning of pure is wrong. It's just not the word that I would choose if I were trying to be precise. On a label, you usually list the botanical name of the oil that you're using. Yeah.
So hypothetically, this in front of us is a bottle, 1 ounce bottle of lavender oil. On bottle today, 10 years from now, as long as it stays sealed, is that going to have the exact same properties, or is it like wine, it can change?
It can change over time. And how much does it change? Depends on, was it stored in a cool, dark place? Was it in the attic? It can also be different for, I would expect wintergreen. Wintergreen, you know, you could bury it in a time capsule. 100 years from now, you come back and the wintergreen is still wintergreen. But it may change from oil to oil how stable it is over time.
Thank you.
Yeah.
Okay, do the color of the bottle really matter?
So some of these will be degraded by sunlight. They typically come in a brown bottle to protect them from light. They're not black bottles because you'd like to be able to see how much is in there. And so a brown bottle is a good compromise. A dark green bottle, and you find the same thing with wine, right? You don't generally find wine in a clear glass bottle because they're trying to protect it from sunlight. Yeah. Or in a box. The box is a perfect protection from sunlight. Yeah.
So not to state the obvious, but there is an infinite number of variables that could affect your calculation at any one time, in any one situation, any of these.
I wouldn't say infinite, but there are more variables than a layperson might imagine. So typically, and I don't want to step on tomorrow's lecture, but there's an organization called ISO. Their whole job is to specify things. That's what they do. So if you want a blender, you know, what is a blender? And they have a specification for not just essential oils, but all kinds of things. What is authentic peanut butter? Okay, that's what they do for a living, is to make up rules for what genuine peanut butter is. And typically an ISO spec contains a dozen different compounds that they look at that it ought to be in this range and not in that range.
Okay, plastic or glass? Does it make a difference?
Okay, it does. And so I'm going to, again, let that question age like a fine wine, and we'll talk about it tomorrow. Yeah.
Okay, looking at that chart, I see, what is eucalyptol and camphor doing in lavender?
You know, you have, when you die and get to heaven, you can ask God that question. What in the world is a lavender plant thinking about when it makes eucalyptol? But if you remember, where do you think the word eucalyptol came from? Eucalyptus, because somebody had to discover that compound first, and they got to name it. And they named it after the place where they found it, in this case. It's also more terrible than that, because eucalyptol is generally known in the trade as 1,8 cineol, or any of another dozen synonyms. So now that multiplies my headache enormously, because you know, I see, oh, this should have eucalyptol between 1 and 8%, and I have 1,8 cineol between 1 and 8%. They're the same thing, and you know, you have to learn that sometimes these compounds have multiple genuine names. So the question on why does a lavender plant produce eucalyptol at all? I don't know. Ask a lavender plant. And different lavender plants, some make it and some don't. And I don't know why, you know, I can't really look in the mind of a lavender plant. All I know is if you look at the 42 different genuine samples of lavender oil, some of them have eucalyptol and some of them don't. And they have varying composition. So the database that we use is academic journal articles about essential oils distilled in the laboratory from that plant right there that was grown in this field at that time of year and harvested and distilled. So the answer is It could be there from contamination, but it's not necessarily there from contamination. Nothing's stopping me from adding extra eucalyptol to my lavender oil, but it doesn't have to be the case.
But don't they come, like sometimes they come in the same family? Like you may not think about lavender being in the eucalyptus family, and then, and that's why it probably contains some of it?
Yeah, but look at this. Look at what else is in here. Limonene. Where do you think limonene, the guy that discovered limonene, where do you think he discovered it from? From lemons and limes. That's where the name comes from. And yet, you expect lavender oil has some limonene. Okay, so GCMS is a powerful tool, blah, 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 blah. Tomorrow we're going to learn about what do the percentages mean and what do they tell us about the authenticity of an essential oil. Before I finish, go ahead and pull your paper out, and what do we conclude from this chromatogram that has developed over the last 40 minutes or so? Just pull it right out. And we had 4 dots there. One was the purple dot, one was the pink dot, the green dot, and the mystery dot. Can you tell anything about the mystery dot?
It has all 3 colors. It's a lot like pink, exactly like pink.
And in fact, that is not just sort of the same pink, it is the same pink. But what else does it have? It also has the green, because that mystery dot was, I wrote the pink dot and then I wrote a green dot right on top of it. So we have a mixture of things. The purpose of the chromatogram is to separate a mixture into its components. Look at the purple dot. I didn't mix the purple dot. I took the purple dot straight out of the pen, and yet you notice something interesting about the purple dot. That purple dot, the ink in the purple pen is actually a mixture of at least 2 different inks. It's at least 2, because look, we got 2 different colors there. Which one has the greater affinity for the water? Blue or purple? Greater affinity for the water. The blue had a greater affinity for the water. The purple had a greater affinity for the paper. They moved at different rates. So what looked like 1 ink is separated into at least 2. How many compounds are actually there?
2.
At least, notice I say at least 2, because do I know there aren't 3? I don't know. It depends on how hard you look. Just like the gas chromatograph, it depends on how hard you look, how many different colors you're going to find. So I thank you for your attention, and we will pick up tomorrow morning with interpreting GCMS reports. Thank you.